Welcome back. In this lecture, we will look at the impedance of an electrochemical double layer capacitor electrode uh, without an assumption we had used in the previous lecture. This is a general circuit for a porous electrode. This refers to the side facing the current collector. This is the side facing the electrolyte. This denotes the resistance in the electrolyte, which is part of a porous electrode. In the previous lecture, we had taken this Rs, that is the resistance of the electronic conductor, to be zero. That is, we had assumed the conductivity of the electronic conductor to be infinity. We are not going to be using that assumption. Without using that assumption, the impedance is as follows. We are not going to derive this formula, but certain parts of the formula should make sense. So impedance is a complex quantity, but the real part of the impedance should be straightforward for you to interpret. For example, this is the real part of the impedance that shows up as resistance from this formula, and there are other features of the formula. So what is new in this formula compared to the impedance of EDLC electrode pointed out in the previous lecture is that this term was not there in the previous formula. That is, this denotes the conductivity of the electronic conductor. All the rest of the terms have the same meaning as what is stated in the previous lecture. So we non-dimensionalize omega in the following manner. Again, the only term that is new is this shows up in the non-dimensional omega. So let's contrast the behavior from what was shown in the previous lecture. All the terms and the parameters remain the same. This was the result from the previous lecture, where there was no resistance for electronic motion. But as opposed to that, we are incorporating finite resistance and finite conductivity. In this case, the conductivity for the electronic motion is infinite, but here you have finite conductivity. When you compare both these curves, you see the following. This curve denotes K by sigma as 0. That is, this for this curve, sigma is infinity, so it should compare to this curve, because for deriving these curves, we had used sigma as infinity. So when you change sigma, that is decrease sigma from infinity, and plot these two other curves, you see the following. So what is important to understand is as omega goes to infinity in this curve, in these all three curves, what you saw was that as omega goes to infinity, the real part of impedance, which is the resistance, it goes to 0. We also interpreted that as the capacitor is not being utilized. Only the front part of the capacitor facing the electrolyte feels the potential drop, and the potential drop does not percolate across inside the porous electrode. Therefore, there's no current inside the porous electrode. So as opposed to that, when you have finite conductivity, so in this case, the conductivity is infinite, that is sigma is infinite in this case. So in this case, with finite conductivity, these curves intersect the x-axis. If you make this to be infinity, it will not intersect the x-axis. So this is one difference. And the equivalent distributed resistance, which is shown here, which is also shown here, takes up this value. So um, as uh, sigma, as omega uh, becomes less than the cutoff, uh, this curves asymptotically reach a particular value for the real part of impedance. That's what we meant by equivalent distributed resistance. For these curves, it took up this value. This looks like a third of the resistance. This is resistance, this is third of the resistance. So here, one more conductivity term is taken into account, and the equivalent distributed resistance, EDR, gets modified via this formula. This is often a more realistic representation of the system compared to this representation. So with that, we are our coverage of the impedance of EDLC electrode is done. We are moving to another brief topic, which is the full cell analysis for an electrochemical double layer capacitor. If you have a full cell, you have two, the overall resistance is sum of the resistances in series. These are the resistances associated with the two electrodes. Then you have another electrode whose dominant, not another electrode, another resistance whose dominant resistance comes from that of the separator. So two electrodes are separated by a separator. This resistance comes from the resistance offered by the separator. So what do we gain from all these analysis? So the equivalent capacitance for a full cell is known. Okay, so we have already shown how to add up the capacitance associated with individual electrodes. The overall capacitance for a full cell is known. With that, what kinds of questions you can answer? So an important question to answer is the capacity of the cell, right? So if given the area, given this quantity, you know this quantity, and if you know how thick the electrode is, you can compute the overall capacity of a particular porous electrode. This is an important quantity which is used, which needs to be specified in practical applications. This is the formula. So this should be straightforward. So this is all true when omega is asymptotically tending to zero, right? That is, when to utilize the porous electrode, we want to be operating at frequencies less than that of cutoff frequency. In such regime, this formula is valid. And we can also ask this question, right? So what is the, once you know all the relevant parameters as discussed in the previous lectures, you know how to think about the cutoff frequency. And we also know what is the implication if you operate above the cutoff frequency or below the cutoff frequency. That is also known from this analysis. So typically, the maximum operational voltage depends upon the stability of the electrolytes, because in the porous electrode, for the current to be transmitted within the porous electrode, there is a potential drop. If the potential drop is significant within the porous electrode itself, this may lead to the breakdown of the electrolyte. So for an aqueous capacitor, this there is a voltage window of about 1.2. You don't want to be operating beyond this voltage window, because water itself might dissociate, which you don't want to happen. So if you want to have a broader, greater voltage window, you typically operate using organic electrolytes. They have their own challenges in the sense that the ionic conductivity of an aqueous electrolyte is typically more than the conductivity of ionic conductivity of a non-aqueous organic electrolyte. So even though you have increased the operational voltage, uh, there are other challenges like uh, less than the conductivity that is seen in aqueous medium. That's a big challenge. So all these things gets into the area of material research. The other issue which people are trying to undertake is how to get hierarchically porous electrodes. Making high surface area porous material has become rather easy, but if you can have structured porous material, that has certain advantages. That is another material challenge which is being undertaken. With that, we close this topic and we move on to analysis of power and energy of an electrochemical double layer capacitor. We'll address that issue in the next lecture. Thank you.